All right, welcome back. Today we're going to talk about 8.2 binomial distributions. Note that the word binomial has the prefix bi or bi, which indicates that there are two possibilities for each case. Okay. All right, so this is a specific discrete probability function or formula for problems with fixed number of trials. So in order to satisfy the condition of being binomial, there has to be a fixed number of trials. There has to be independent trials. Remember what independent means is that the probability of the next one occurring is not affected by the probability of the last one occurring. There's only two possible outcomes, a success and a failure. Also, each trial is independent and the probability of success I put in quotation marks because it doesn't necessarily mean a good thing, is the same for each trial. So not only are the trials independent, but the probability of success has to be exactly the same each time. We denote P as the probability of success and 1 minus P is the probability of failure. Q is the alternative for 1 minus P. We don't use F, we use Q. All right. X is the number of successes with n trials. Examples, flipping coins. So maybe flipping a coin 10 times. The probability that x is equal to 5 means exactly 5 tails or heads. The example we gave earlier was heads. So what is the probability of exactly 5 heads out of 10 tosses? And the answer might surprise you. You might think the answer is 50%, but it's not at all 50%. It turns out that the answer is 24.6%. So you might wonder, well, wait a minute. 5 is half of 10, right? So why wouldn't it be 50%? Well, that's what we're going to talk about with the binomial. Other examples might be clinical trials for drugs and defective samples in a product line. Okay, so we're going to look at a couple of different examples. One of them will be health related. Okay. Before we can get to the binomial formula, though, we need to talk about the fundamental counting principle, or FCP. Fundamental counting principle basically says that if you have n ways that one certain event can occur and m ways that the next event can occur, then there's going to be n times n ways for both events to occur. Sorry, that was my phone. All right, so this is I don't know if this is readable, but it says, for a sequence of n experiments where the first has k1 outcomes, second has k2, and so on, we multiply the number of outcomes. We multiply the number of outcomes. So a quick example of this might be if let's say I have outfit. I'm talking about outfits. In other words, wardrobe. Yes. And in my wardrobe, I have 8 shirts, 4 pairs of pants, 5 different kinds of socks, and 2 pairs of shoes. So then the question we could ask is, how many different outfits could I wear? This is a classic example of the fundamental counting principle. So earlier we had talked about K1, K2, and so on. And the number of ways, or in this case the number of outfits, is simply the product of each of the kinds of things that I'm wearing. So shirts times pants times socks times shoes. So I would simply go 8 times 4 times 5 times 2, 320. Now in this class, and in many classes where we have word problems, you don't want to just say equals 320. You want to say there are 320 possible outfits that I can wear based on that information. So try to give the answer as a sentence. Okay? When it's being asked as a question with words, give the answer with words. Don't just give a number. So another example, we have area code made up of 3 numbers, 1, 2, 3, or first, second, third. Now when I say area code, that's like 253 or 360, which are a couple of the area codes in Washington, yes? So, but one of the rules is that the first one cannot be a 0. So the choices are 1 through 9 for the first one. So I have 9 choices for the first digit, okay? But the second and third can be any digit I want. So remember, 0 through 9 includes the 0, so that means 10 choices here. So that means I have 10 choices for both the second and the third digit. So 900 area codes. Now, if 900 area codes get used up in a particular country, that's when they would need to add a digit to the area code. So if the population in the United States continues to grow, at some point we may have 4 digits for the area code. But as it stands now, we just have 3. A doctor has 9 people in the waiting room and can take 3 of them in the next hour. How many different ways can the doctor see the patients? 9 people in the waiting room, and we're going to take 3 patients in the next hour. So we've got 3 patients. There's 9 to start with. Okay, but one of the patients has been seen at that point. So for the second choice, there's only 8 people to choose from. And for the third choice, there's only 7. So we would say 9 times 8 times 7. That's how many people we have to choose from, 504. So there's 504 ways to see the 3 patients. By the way, you may have heard the term combination lock. If you ever had a locker in high school, the combination lock was probably a dial that started at 1 and went all the way around to maybe 36 or something like that. So, but as you recall, you turn the lock to the right, to a certain number, then you turn it to the left, and then you turn it to the right again. But the numbers can repeat, so you might ask the question, how many combinations? Or how many, we say combinations, that's the word that we use, right? Well, this is the fundamental counting principle. So 36 for the first, 36 for the second, and 36 for the third. I know this because my combination lock in high school actually was 36 to 36. It was easy to remember. So I had a repeat, right? So numbers were allowed to repeat. So 36 to the third power is 46,656 combinations. However, later on we're actually going to have the definition of a combination is actually going to be that you cannot repeat, right? And the order is irrelevant. So one of the things that I joke about in my classes is that technically this should not be called a combination lock. It should be called a fundamental counting principle lock. Hardy har har. Anyway, so just something to think about. All right, factorials. When we use the the exclamation point, right? This is a definition here. So n factorial means an n needs to be a counting number. Like 1, well, it could be 0 also, 2, 3, 4, and so on. You would take n and multiply by the number before it, called the predecessor, times its predecessor all the way down to 2 and 1. So 4 factorial, for example, would be 4 times 3 times 2 times 1, which is 12 times 2, which is 24. Okay, so that's what we mean when we say factorial. The exclamation point in math means factorial. All right, so the shortcut for this would be to use the calculator. First, you would type in the number that you're going to take the factorial of, let's say 8. Then you click the Math button. Then go over to the PRB menu. I use the left arrow. You could go right 3, or you could just go left 1. And then there's the exclamation point right there. That's the factorial key. Then hit Enter, and then we have it. So 8 factorial, I forgot what it was, 40,320. Yeah, 40,320. Now, we should also keep in mind that 0 factorial is 1. We have to have that, otherwise things won't work out the way we want them to. All right, earlier I was talking about the word combinations. Now, combinations don't work the exact same way as fundamental counting principle. We're actually going to choose R distinct objects from N. So N is the total, right? R is how many we're choosing, when order is not important. Okay. So the example of the 3 patients from 9 doesn't work in this case because the order mattered, right? So if we chose Betty on the first patient and Kim for the second patient and John for the third, that's not the same thing as choosing Kim and then Betty and then John. It's the same for John, but not for Kim and Betty, right? Maybe Kim has a more severe problem in the ER and needs to be seen first, right? So these are what we would call those permutations. But combinations are basically sets of objects taken 3 at a time, 4 at a time, 5 at a time, or R at a time, and it doesn't matter the order. Okay? So an example of that might be if I make a group in the class, and let's say that the group consists of Albert, Bonnie, and Charlie. Okay? That's the same group as if I had chosen Bonnie, forget what the A name was, Andy, whatever, and Charlie. Okay? They're the same group. So the order that we list the group members is irrelevant. Okay? So that's what we mean. So that's what combinations. So combinations, we're counting how many of these there could possibly be. All right? So this is the formula for it. It looks kind of complicated, but it basically says we're taking n factorial, okay, so the number of things that we're choosing from factorial, divided by r factorial multiplied by n minus r factorial. There's also a calculator command for this as well. All right, so at a cafeteria, Joe can pick 3 different vegetables from a choice of 8. Again, order doesn't matter because, you know, those 3 vegetables that are on the plate, let's say broccoli, carrots, and peas, right? If he puts broccoli on his plate first and then peas and then carrots, it's the same as putting the carrots and then the peas and then the broccoli. So the order is irrelevant, okay? So we would say 8C3. That would be, so in this case, N is 8, R is 3. Okay? So the way we can do this using the formula, let me just see what we've got here. Yeah. So in this case, N is 8, R is 3, 8 minus 3 is 5. But there's a way that we can do this a little bit simpler. Remember that the factorial, 8 factorial, means 8 times 7 times 6 times 5 times 4 and so on. But there's a 5 factorial in the denominator. So cancel the 5 factorials. 3 factorial means 3 times 2 times 1. Then you can simplify. 8 divided by 2 is 4. 6 divided by 3 is 2. So now I just have 4 times 7 times 2, which is 28 times 2, which is 56 choices of 3 vegetables. Okay, so that's the number of combinations of 3 veggies that he can choose from a choice of 8. So if you're at a salad bar and there's 8 different kinds of veggies, there's 56 ways that you can have 3 of those. Okay, so that's an example of combinations. So this formula is actually going to be used in the binomial distribution formula. So we have to know what combinations mean so that we can realize what these numbers, where these numbers come from. Okay? If I toss a coin 4 times, what is the probability of getting exactly 1 head? Right? Well, there's exactly 4 ways that we can get exactly 1 head in 4 tosses, which are H, T, 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 H, T, 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 H, T, and T, 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 H. Notice there's 4 ways to get exactly 1 head. Okay? So in order to determine the probability, I have to know how many ways there are to get that event, and I have to divide by the total number of probabilities. So this is the fundamental counting principle to determine the denominator. So there's 2 possibilities, heads and tails for the first toss, 2 for the second, 2 for the third, and 2 for the fourth, for a total of 16. So that means the denominator is going to be 16. Okay? So each one of these has a probability of 1/2 or 0.5. So the probability of any of those 4 happening, because those are disjoint events, we can add their probabilities. Right? So 0.5 to the 4th is 0.0625. Right? And so if we add those 4 numbers together, so remember that 0.5 to the 4th is the same as saying 1/2 to the 4th, which is the same as saying 1 over 16, right? So this is the same as 1/16. So this is 1/16 plus 1/16 plus 1/16 plus 1/16. So hopefully that makes a little bit more sense as to why that's the probability for each of those. Because each one is, there's 1 way to get HTTT out of a total of 16 possibilities. There's 1 way to get THTT and so on, right? So what I get is 4/16 or 25%. So the probability of getting exactly 1 head is 25%. So we're looking at this example a little bit different way than we had looked at it before, so that we can start to understand where the binomial formula comes from. So when we're calculating the probability of a certain number of, let's say x is equal to little x for the binomial, we have to use the combinations of the n items selected little x at a time, we also have to use the probability of success in one trial and the probability of failure in the rest of the trials. So that's where the formula comes from for the binomial. Now, the nice thing about this is that you don't really need to memorize this formula because there's a button, there's a distribution on the calculator that enables you to do it. But it's always good to look to see where things come from. All right. So here's the same formula that I was just talking about. X is the number of successes, n is the number of trials, and p is the probability of success on each trial. Now, as I mentioned before, success is not necessarily a good thing. It just means whatever x is defined as, whether it be heads when you're tossing a coin, whether it be getting a 4 when you roll a die, that's the definition of success in that case. Okay. So what is the probability of getting exactly 6 heads in 10 coin tosses? Let's see. Yeah, I just want to make sure I don't run over it. So the probability of 6 heads. So in this case, what's n? 10 coin tosses. What's little x? 6 heads. Okay, so the probability of success, of course, is 50%. So this is going to be n c x, this should be x, not r, times p to the x times the probability of failure means the probability of getting a tails to the n minus x. So if I'm bringing that up on the calculator, it'll be so here's how we do combinations in the calculator. Math, probability area, NCR. There's the combinations. Taken 6 at a time. Okay, 210. So there's 210 ways to get 6 heads, okay, out of 10 tosses. Then I need to multiply that by 0.5 to the 6th and 0.5 to the 4th. Now it's worth noting that 0.5 to the 6th times 0.5 to the 4th can be written as 0.5 to the 10th. But that's only true because the probability of success and the probability of failure are exactly the same thing. Okay, so in general, they're not necessarily going to be the same thing. So enter 20.5%. So that means 20.5% of the time, or about 21% of the time, we expect to get exactly 6 heads in 10 coin tosses. Okay. So now we're changing the probability. This is just a generic binomial. We can do this on the calculator by using the binomial distribution here. So you go to the DISTR menu, which is second variables. Then you go to letter A, which is binomial, 0, which is binomial PDF. Okay, CDF means cumulative distribution function. PDF means probability distribution function. So PDF will give you an exact number of successes. Okay, so the way we do that, the way we type it in, is we use an open paren, and we type in n, and then a comma, and then p, probability of success, and then x. If we're doing a cumulative, we use, and by the way, that's the probability of exactly x successes. Same thing for binomial CDF, but that's the probability of at least, I believe it's at least x successes. Okay, so say in the example of the heads, if I was to say the probability that x was at least 6, that means 7 or 8 or 9 or 10 heads, which, as you know, since they're disjoint, would be the probability of 7 heads plus the probability of 8 heads plus the probability of 9 heads plus the probability of 10 heads. Okay, so that's, if I was to use this with n is 10, p is 0.5, and x is 6, it should give me the answer to this question without having to do all that extra work. Okay. Erase that. All right, so we are calculating the probability that x is exactly 6. So we will go binomial PDF, n is 10, comma, p is 0.2, comma, x is 6, close paren. 0.0055 or 0.55%. Okay. All right, let's go probability that x is equal to 7 when the probability of one success is 43% and n is 9. So once again, binomial PDF 0, or you could just click the 0 button, right, if you remember it. N is 9, comma, 0.43, comma, 7. 3.2% approximately. Okay, so that's how we do the binomial distribution on the calculator. A quality control expert at a large factory estimates that 10% of all batteries produced are defective. So success, in this case, we have to think about what does that mean, and then what's the probability of success. Okay. If he takes a sample of 15 batteries, so n is 15, what is the probability that exactly 2 are defective? So little x is 2. So we're looking for the probability that x is equal to 2. Okay. So the success in this case means that we have a defective unit, which sounds sort of counterintuitive. Remember earlier I said it doesn't necessarily mean something good, but it is good if we catch that it's defective and then we don't sell it, right? If we means the company, right? Probability of success is the 10%. So there's a 10% probability of each individual unit being defective. Okay? So little p is 10%. So we would use the binomial distribution once again. Second distribution, 0. N is 15, comma, 0.1, comma, exactly 2, close paren, 26.7%. Probability is 26.7% that 2 will be defective. Okay. Now, at most 2. So this is something you may have looked at in Math 96 or possibly even Math 54. What does at most 2 mean? Well, if it helps to look at the number line starting with 0, 1, 2, and so on. So is it pretty clear that 0 is the least number of the batteries that could be defective, right? Can't have -1 that are defective. So at most 2 means 2 is the largest or the most amount of batteries that can be defective, right? And 1 also counts for that, and 0 also counts for that. So at most 2 means that x is less than or equal to 2, which means that x is equal to 0 or 1 or 2. Okay? So at most 2 means this. So the probability of at most 2 is the probability that x is 0 or 1 or 2, which is the probability that x is 0. In other words, no defective units, plus the probability of 1 defective unit, plus the probability of 2 defective units. That's how we would calculate it if we were using the binomial PDF. Okay, p of 0 plus p of 1 plus p of 2. Now, we already calculated that, right? That was the 26.7%. So all we have to do is calculate this, and then we're done, and add those three numbers together. So we've got the 26.689%. We could also go distribution 0, 15, 0.1, that hasn't changed. 0 are defective. Is 20.6% approximately. And then one more time. 15, 0.2, 1. Okay, so what I want to do then is add these three numbers together, right? So I would say plus 0.20. You don't have to write the whole number, just enough digits to where you don't lose the number. Plus 0.26689 or 26690. So if I add those together, that's the probability, 60.5%, that at most 2 of those batteries will be defective. Probability that at most 2 batteries will be defective. Okay? All right. What is the probability that a family with 6 children has more than 2 girls? Assume that the gender of one child is independent of any. So, and also assume that the probability of a girl is 50%, and the probability of a boy or complement of girl is also 50%. So little p is 0.5, q is also 0.5. Okay. So let's determine what n is, what little x is, and little p we already know. Okay, so x, in this case, we want more than 2, right? So the probability of x being more than 2 is the same as the probability that we have at least 3 girls, which is the same as the probability of 3 girls, or 4 girls, or 5 girls, or 6 girls, which is the probability of 3 girls plus the probability of 4 girls plus the probability of 5 girls plus the probability of 6 girls, given the fact that they are independent and disjoint. Okay? So we would add up all of those probabilities. But if we use the binomial CDF, we don't have to do all of that work, right? So we would say n, which is 6 children, comma p, 0.5. In this case, I believe x is 3, right? Because it's the probability that x is at least 3. So I would say distribution. This time we're going to do binomial CDF, which is the A key. Now A is the alphanumeric key here, so you could say alpha math, I believe. Let's try that, see if it works. Alpha A. Yep, it worked. Okay. So 6, 0.5, 3. 65.6%. So what that means is that any family that has 6 children has a 65.6% probability that they'll have more than than 2 girls. Okay? So that's how we do that. So you could either calculate each of these individually and add them together, or you could just use the CDF. So keep in mind that the CDF only uses the greater than or equal to sign. Okay? It only uses the greater than or equal to sign. So if I wanted to calculate the probability that X was less than 5, for example, fewer than 5 girls, what I would want to do is use a complement rule. So 0, 1, 2, 3, 4, 5, or 6. These are the possible number of girls that the family could have, right? So less than 5 would be either 4, 3, 2, 1, or 0, okay? But that's 5 different things to calculate, and I can't directly use the CDF because CDF uses greater than or equal to. But what I can do is say that's 1 minus the probability that X is greater than or equal to 5, right? Because 5 and 6 accounts for greater than or equal to 5. So this I could use the binomial CDF. I could say second distribution A, 6 kids, 50-50 chance per kid, and 5 is 98.44%. But if I subtract that from 1, so 1 minus answer, that gives me my answer. So the probability of fewer than 5 girls is the probability of fewer than 5 girls is 0.015. That doesn't seem to make sense. Well, anyway, I would have to check that. But anyway, the point is, if I say the probability that X is less than R, that's 1 minus the probability that X is greater than or equal to R, okay? So that will help you narrow that down and not have to calculate so much. The National Institute of Health estimates that there's a 20% chance of an adult American suffering from a psychiatric disorder. 4 randomly selected adults are examined. So N is 4, P is 0.20. So success in this case is not such a good thing. They're suffering from psychosis or whatever. So the definition of success is the randomly selected American the selected person suffers from a psychiatric disorder. And the probability of success is 20% chance. Okay? What is the probability of exactly 3 out of 4 people having psychotic disorders? So that would be 3 out of the selected 4 people. Okay, so this would be binomial PDF 4, 0.2, and 3. So I think the 0 was, so 4, 0.2, 3. 2.56%. Okay, so it's low, it's expectedly low because each person only has a 20% probability, and we're saying 3 out of 4 people. That's extremely unlikely. And so this illustrates the fact that it's extremely unlikely. So any group of 4 people has a 2.56% chance of having 3 of them with a psychotic disorder. Probability of 3 out of 4 people having the psychotic disorder is 2.56%. What is the probability of exactly 3 out of 4? We just did that. What is the probability of 3 or fewer having disorders? 3 or fewer, once again, means 0, 1, 2, or 3. So again, you could either add those up, or you could use the CDF for that. All right. And that concludes the presentation.